Up till now, we studied single MOS based LNAs. In this lecture and in subsequent one, we will study multiple MOS based LNAs. So here we are going to study Cascode LNA. We are quite familiar with Cascode structure, which has higher gain compared with a common source, and it has better reverse isolation. That means any signal entering into the amplifier from output side will have difficulty in reaching the input side. So we will today study uh, under which condition a cascode can be used as LNA. That means first we will find out Z in, and then we will find out noise factor. So let us first draw the cascode structure. So we are familiar that this cascode is basically cascade of a common source. And as the name suggested, this is inductively degenerated cascode. That means the source of the first MOS M1 is degenerated by an inductor. And so the M1 is have the same configuration as we found for the inductively degenerated case. So first stage is similar to or same as what we analyzed earlier. So here we see that this M1 is in common source configuration, M2 is in common gate configuration. So for this case, we want to know what is Z in. That means looking from here, what is the input impedance. So of course, we can carry out the detailed analysis by substituting M1 and M2. But we will not do that. That is going to be tedious, but we will take one shortcut. And recall that when we were trying to find the input impedance of inductively degenerated common source LNA, it is this ID LNA. So here, when we were trying to find out Z in, the output side only allowed this certain current to exist. So this was the circuit that we analyzed to find out the Z in of ID case. And here it did not matter. I mean, whatever was connected here had actually no impact on Z in of this ID, inductively degenerated LNA. So all that mattered was that this current is present here. So here we can see that we have M2, and certainly this current will exist on this drain side of M1. So we can guess that even though we now have M2 connected to the drain of M1, the input impedance is going to remain unaffected. So what will happen here is that this was the Z in of the ID case, the general Z in. So this is what we had derived for the case of inductively degenerated case. So here also we will get the same expression as M2 will allow certain current to exist on the drain side. So input side will be exactly same as that of the ID case. And here we found that uh, this part is real while this part is imaginary. And we found that at omega such that this imaginary part, imaginary of Z in ID is equal to 0, Z in reduces to a real number equal to this. And this frequency will be given by this. From here we can find out it will be XLG minus XCGS1 plus XLS is equal to 0. And this we had already worked out, and this will turn out to be omega is equal to 1 by square root Lg plus Ls into CGS1. So at this frequency, Z in will be equal to Gm Ls by CGS1, which turn out to be omega T1 Ls. So this is for MOS M1. So this is also going to be Z in for ID Cascode. So for match case, this Z in ID Cascode, which is omega T1 Ls is going to be equal to Rs. So we will be using this equation in subsequent derivations. So here also we find that the real impedance is possible, but only at one specific frequency. So this Cascode LNA is also going to be narrow band. Now we will try to find out the noise factor. So here, when we look at the circuit, we see that there are now three noise sources present in this circuit. First is this RS, second is MOS1, and third is MOS2. So we will have to find out short-circuited output current due to each of these three elements. And since all these three are three physically separate elements, so their short-circuited output current and the noise current source, they are going to be uncorrelated. So the mean square of the total is simply going to be sum of the mean square of the individual currents from these three elements. So general procedure will be what we have been following. That means you take up one noise source at a time in the circuit by using the superposition principle, and then try to find out the short circuit output current, and do this for the remaining ones also. So here we are going to do that, but now we have two more. So of course the circuit is going to be a bit larger, and we will have to deal with more number of equations. So first we will try to find out the short circuited output current. Due to Rs, and as usual we will call it ION. So for this case, first we will have to draw the equivalent circuit. So gate of the second MOS is grounded, AC grounded. And this is the current we are looking for. And this is the noise source due to RS. So in this circuit, we want to know what is ION. So here we have drain 2. This is source 2. And this one is source 1. And this node is drain 1. So drain 1 and source 2, they are shorted. So here we have ION, and ION comes here, and it gets splitted into two different currents. We will be calling them as IB and IA. So this IA comes here, and this VN gives rise to a current, a IN. And so here we have again IN, and then here we have IL, this current into the degenerated inductor. So now we are going to set up equations for solving for IUN. So there are going to be set of equations, and we will start with the drain 2 node. First, we will write ACL at drain 2. So that gives rise to a simple equation. IUN is equal to GM2 VGS2. So here, what we have is unknown VGS2. So for this, we will have to set up equations. This we can call, let us say, equation 2. And this is equation 1. So we will be very often requiring this equation 1. So this is equation 3. Now we will set up equation at source 2 for VGS2. For finding VGS2, we will set up KCL at source 2. So this gives rise to IA. Source 2 means IU here IUN is equal to IA plus IB. So IUN is equal to IA plus IB, and IUN is GM2 VGS2, and IA is equal to GM1 VGS1, right? And IB is current flowing through this capacitor CGS2, where we have voltage VGS2. So this VGS2 divided by CGS, reactance of CGS2 gives IB with negative sign. So minus VGS2 divided by minus JX CGS2, where X CGS2 is 1 by omega CGS2. So we have taken J term outside. So here we get GM1, VGS1 minus J VGS2 divided by X CGS2. So from here we can set up equation for VGS2 as GM2 plus J by X CGS2 is equal to GM1 VGS1. So now we have a known VGS1. So for this case, so what we are doing is we are going to designate X CGS2 for J divided by omega CGS2. That means the complete reactance. So we'll keep in mind that this X CGS2 is basically an imaginary element. So this is imaginary. So if we do this, then we won't have to worry about all those signs. So this becomes minus, and this becomes plus. Now it is okay because J part is inside X. Okay. So this will prevent all these confusions. Okay, so we have absorbed the X J part into X, and we are now using this designation for the reactance. So here we now have VGS2 in terms of VGS1. So we'll have to now set up equation for finding VGS1. So VGS1 we can see is this voltage, which is arising because of IN flowing through XCGS. So therefore, VGS1 is simply equal to IN flowing through XCGS1. And keep in mind, once again, XCGS1 is 1 by J omega CGS1. That means J part is also inside X. So XCGS is imaginary quantity, not the real. So now we need to find out what is IN. So we will find out IN and then we will backtrace from here to here, and then VGS2 finally ION. So we need to find out what is this IN, this current. And recall that looking from this reference point towards the right hand side, the input impedance is equal to RS for matched case. And this is the case we are interested in. So IN will be simply Vn divided by 2RS. So therefore, for match case, IN is simply Vn divided by 2RS. So from here now we find that VGS1 is Vn divided by 2RS into XCGS1. Now we substitute VGS1 here to find out VGS2. So what we get is, and we can name all these equations. So up to 3 we have already named. So this one is say equation 4. And so now we go to equation 4. And this is 5. So from 5, 4 becomes GM2 plus 1 by X CGS2. VGS2 is equal to GM1 XCGS1 by 2RS Vn. So from here we can find out VGS2 as GM1 XCGS1 Vn divided by 2RS into GM2 plus 1 by X CGS2. So now we can go to our first equation, the KCL at drain 2, that is equation number 3. We have now determined VGS2, so we can find out what will be RUN. And by the way, this is GM2. So therefore, from 3, RUN becomes GM1, GM2, X CGS1, Vn divided by 2RS GM2 plus 1 by X CGS2. So here we can substitute X to write exact expression for capacitances. So this is GM1, GM2. This XCGS1 will actually come into denominator with in the form of capacitor. So this become 2RS J omega CGS1 and GM2 plus J omega CGS2. So here we see that we have GM1 and CGS1, so they can be combined to write omega T1, the threshold frequency of the first MOS. Similarly, we have GM2 and CGS2, so they can also be used to write omega 2. Right? So if we do all these things, then what we get here is omega T1 for GM1, omega T2 for GM2, then usual Vn divided by 2RS, and then omega from here remains omega, and then GM2 is it will become 1, and similarly this can also be converted into omega 2 and omega. So this will give rise to omega T2 by omega J. So this is what we will get, and of course there will be omega square because we have taken this whole thing common. Actually, there will be then minus sign here. So we take this much common and we arrive at this equation IUN. Now, if you see the mean square, this is what we will be using actually. This is going to be IUN. Mean square is equal to omega T1 whole square, omega T2 whole square, Vn mean square 4 RS square omega 4 1 plus omega T2 by omega whole square, where omega T is Gm by CGS. So this is the exact expression for short-circuited output current due to RS. Now we try to find out the short-circuited output current due to MOS 1. So now we draw the model by including the noise source of MOS 1. So this is noise source due to MOS 1. And we are interested in finding out this current IO D1. So now there are various currents involved here. We will have to again label them. So this is again going to be IO D1, and this is splits into two currents. We will be calling them IA, IB. IB further splits into two currents, say I1, I2, and we again have IB here, which gets divided into again two currents, I3 and I4. So we again start from D2 node. This is D2. So we find IOD1 is equal to GM2 VGS2. We just call it equation 7. Now to find VGS2, we set up equation KCL at source 2. The source 2 is this one. So here we have GM2 VGS2 is equal to IA plus IB. And this IA is because of voltage VGS2 and capacitor CGS2. So IA becomes minus VGS2 divided by XCGS2. Again, XCGS means 1 by J omega CGS, whether it is 1 or 2, plus IB. So now we need to find out this IB. This is unknown. So for this, we will have to write equation, that is KCL at for IB, KCL at D1. So D1 is this node. So IB gets divided into I1 and I2. So IB is equal to I1 plus I2, where I1 is this dependent current source, so GM1 VGS1. So then we will have to write VGS1 GM1 VGS1 plus I2. So now we have to find out what is VGS1. So we know VGS1 is current I3 flowing through CGS. So this is VGS1. So VGS1 is minus I3 flowing through CGS1. And now we have to find out I3. So for I3, so I3 is generated uh, because IB gets divided into two currents, I3 and I4. So we have already encountered this scenario. That means we have two impedances. So this is I3, this is I4, and incoming current is IB. So this Z1, Z2. So we have already done this part, and we found that I3 is going to be IB into Z2 divided by Z1 plus Z2. And note that Z1 is RS plus LG plus CGS1, while Z2 is only LS. So we can write I3 as X LS, this is Z2 divided by X LS plus Z1, which is X CGS1 plus X LG plus RS. So this whole part is Z1, this is Z2, and this is into IB. Now recall that we are going to use this for the match condition, and for match condition this is going to be 0. So this I3 then simplifies to XLS divided by RS into IB. So this is the simplified expression that we get for I3. Now we can go to this equation, which should name. This is 7, then we can call this as 8, and we can call this as 9. And by the way, I2 is ID1. So we can call this as in fact 9. And this is not this as 10, but you can use this one in this equation to get VGS1. So we can call this as 10, this as 11, 11 and 10 imply VGS1 is equal to minus X LS X CGS1 IB divided by RS. Now once VGS1 is known, we can go to equation number 9 to find IB. From 9, we get IB is equal to minus GM1 XLS X CGS1 divided by RS IB plus ID1. So this becomes 1 plus GM1 XLS X CGS1 divided by RS into IB is equal to ID1. So here we need to see that what is this? Can it be further simplified? And answer is yes. So here we can write 1 plus GM1. This becomes omega LS divided by omega CGS1. Now here omega cancels out. So GM1 divided by CGS1 is actually omega T1. So this is 1 plus omega T1 LS by RS into IB is equal to ID1. And keep in mind that for match case, this numerator is equal to RS. So this becomes 1 plus 1 IB is equal to ID. 1, that means IB is equal to ID1 by 2. And here we found that this factor is equal to 1 for match case. Actually, we will encounter once again this in subsequent derivation. So we will keep in mind that GM1 XLS XCGS1 divided by RS is actually equal to 1. So we will straightway use this in the later derivation. So here we find that IB is half of ID1. So what it says is that in this circuit, this current is half of ID1, which is this one. So we had exactly same result for the inductively degenerated LNA, where this was shorted. So when we shorted it and tried to find out the contribution of the MOS to the short circuited current, we found that it was ID by 2. So we are again getting the similar kind of result, but this time it is not shorted. Drain 1 is not shorted, rather it is connected to another MOS. But we still find that half of the ID sort of circulates in this one, and only the remaining half actually flows to MOS 2. So this might not be very surprising result. So this is IB, but this is not the final destination. Final destination is to find out short circuited output current IOD1. Okay, so once we have found out IB, we can go back to find out VGS2, because this is equation 8 is the starting point where the unknown was IB. So IB we have determined. So we can go to equation 8. So we get GM2 plus 1 by X CGS2. VGS2 is equal to ID1 by 2. So that gives rise to VGS2 is equal to ID1 by 2 GM2 plus 1 by X CGS2, which is J omega CGS2. Now, once we know VGS2, we can find out IOD1, which is GM2 into VGS2. So IOD1 is GM2 ID1 divided by 2 into GM2 plus J omega CGS2. So we can take GM2 common, and we will get 2 into 1 plus J omega by omega T2, where omega T2 is GM2 by CGS2. Therefore, mean square current IOD1 is ID1 by 4 1 plus omega by omega T2 whole square. So here you can see that when the threshold of the second MOS is very high compared with the operating frequency, then this might get approximated to ID1 mean square by 4. This is what we had got for inductively degenerated case. Now, and the third and the last current that we have to find is due to MOS 2. We will be calling it as IOD2. So now we include the noise source only for the MOS 2. Which is ID2, GM2, VGS2. And we have now GM1, VGS1. This is LS and CGS1. Here. So here also we will label various currents. So IOD comes and splits into these two currents and combines here back to again give rise to IOD2, which gets splitted into two currents, I2 and I1. And this I2 again gets divided into I3 and I4. So these are the various currents which we might have to find out. This is drain 2 and this is source 2. So now let us set up equation. So starting will be KCL at drain 2. So that gives rise to IOD2 is equal to GM2 VGS2 plus ID2. So let us call this as equation 13. Now for finding out this VGS2, we will set up for VGS2, we set up KCL at source 2. So at source 2, we see that IOD again splits into two currents, I1 and I2. Where IO2 is equal to GM1, VGS1, and I1 is because of VGS2 voltage and CGS2. So we find that I1 is minus VGS2 divided by X CGS2. This is I1 and I2 is GM1 VGS1. So here now we have to find out VGS1. So we have set up equation for VGS2, but now it involves VGS1 also. So we have to do something about VGS1. So now for finding VGS1, we note that VGS1 is basically this voltage which arises because of I3 flowing through CGS1. So VGS1 is negative of I3 and X CGS1. So we have to now find out I3. So we again see the current division phenomena taking place here. This incoming I2 current getting divided into current I3 and I4 for two impedances, Z1, which is RS, LG, and CGS1, and impedance Z2. So we know that I3 will be X LS, the impedance 2 divided by impedance 2, that is XLS, plus impedance 1, which is X CGS1 XLS plus RS, and the incoming current, which is I2. And what is I2? I2 is GM1 VGS1. So this is I2, right? So here we see that we again encounter this three terms, three reactances, which are going to be 0 for match condition, for matched case, right? So we take the help of this observation and write VGS1 is equal to minus XCGS1 XLS, and now we substitute I2 by GM1 VGS2 divided by RS. Right. So here we are again encountering this term which we have already encountered earlier, namely this factor. And we saw that this gets reduced to actually omega T1 LS by RS, which will be, sorry, this is VGS1. And this is going to be equal to 1 for match case. So what we find is 2 VGS1 is equal to 0. This implies that VGS1 has to be equal to 0. So this is match case equal to 1. So we find that VGS1, this voltage is equal to 0. Right? And we had related this VGS with I2. So we saw that VGS2 is, sorry, VGS1 rather, 1 is equal to part of I2, which is I3, that was XLS I2 divided by XLS plus XCGS1 plus XLG plus RS. So this is I3 flowing through XCGS1, and in fact it's a negative. So this is the relation between VGS and I2. So since VGS is 0, that means I2 is also equal to 0. Right. So we will be calling this as equation 14. Right. So now we know that VGS 1 is 0. So we can find out IO D2 from here, from this equation, where this VGS1 is equal to 0. So IOD becomes simply equal to this first factor. Therefore, IOD2 is equal to minus VGS2 divided by XCGS2. So this gives us VGS2. This is the first parameter that we started to find out. Now we substitute this into here, equation number 13. So this is the unknown which we have already found out. The starting point was this one. So now 15, 13 becomes IOD2 is equal to minus GM2 X CGS2 IOD2. This is IOD2 plus ID2. So 1 plus GM2 X CGS2 into IOD2 is equal to ID2. So from here we can find out our desired unknown quantity ID2 divided by 1 plus GM X CGS2, which can be written as 1 plus GM2 divided by J omega CGS2. And this can be written in terms of omega T2, 1 plus omega T2 divided by J omega. And therefore the mean square of D2 divided by 1 plus omega T2 by omega whole square. This. So we have found out all the three current components and their mean square. So here you can see that when omega T2 is significantly greater than omega, this IOD2 mean square simplifies to ID2 mean square divided by omega T2 by omega square, which is omega by omega T2 whole square into ID2 mean square. That means as the gap between operating frequency and omega T2 increases, the noise contribution of the second MOS is less and less. So now we can finally find out noise factor. So total output noise power is going to be proportional to sum of these mean square currents divided by output noise power only due to RS, which is proportional to this quantity. So noise factor becomes 1 plus IOD1 mean square plus IOD2 mean square ION mean square. Now if you substitute the exact expression for each of these three terms, what we will get and carry out the manipulation, we will get gamma 1. So we are going to get this as ratio 1, this as ratio 2. There are going to be two terms. So this first term will give rise to gamma 1 GD0 RS omega by omega T1 whole square. So this is from the first term. Now the second term is going to give rise to this expression 4 gamma 2 GD02 RS omega by omega T1 whole square and omega by omega T2 whole square. So here we see that this third term is fourth order in omega by omega T, while this second term is second order. Right, so as the omega by omega T ratio widens up, this third term is going to be very, very small, and one can, for majority of the cases, make this approximation. This is GD01. And recall that this is actually exactly equal to noise factor of inductively degenerated LNA. So here we see that noise factor of inductively degenerated cascode. So this is ID cascode is approximately equal to that of the ID case. So we have already seen that the ID case is the best in terms of noise performance. So this Cascode one is as good as ID. Very surprising because we have now two MOS. So contribution of second MOS is very less, and we have now more gain also, and better reverse isolation. So for reverse isolation, we can see that we have derived this I2 is equal to 0 here. So for this circuit, it says that this current is going to be 0. That means if there is something entering into this amplifier, so it will not reach to the output side. So this is the meaning of reverse isolation. And this is happening because of this I2 is equal to 0. So sort of both gates isolated. And this is also desirable property, so that this amplifier doesn't radiates back. That means receiver doesn't become a transmitter, unwanted transmitter.